Good afternoon, everybody. Can you hear me? Good
Yes,
afternoon, everybody. Can you hear me?
yes, Professor.
Yes,
Okay,
sir.
good. Good afternoon, everybody, and welcome to ECE 580, which is the makeup lecture. I hope all are safe and healthy. Let's continue our discussion from last time. We started talking about frequency response, frequency response methods in control system design. And control system design. We started, of course, with the analog system, as I will review it very quickly to you before we go to the digital. We said that we do have two types. The first one is referred to as the Nyquist plot. And this is a what? A single plot using polar representation of the frequency response of the open loop transfer function. Of the open loop transfer function. By the way, I might forget to move the paper up and down. You need to let me know. You need to let me know to move the paper up and down. Now, what does that mean? We have G of S, which is a transfer function of the open loop. The loop looks like this, by the way, the analog loop or the analog system. This is C of S, which is the controller. This is what? The plant, which is GP of S. And we have a unity feedback system. This is R of S. This is what? Y of S, the output, and its unity feedback system. Notice that everything we are going to do today and in the final exam will be assuming that we do have a unity feedback system. But if our system is not a unity feedback system, we could always change it to a unity feedback system, like I showed you in the middle of the semester. I don't know, 3 or 4 lectures ago. I showed you how to change a non-unity feedback system to a unity feedback system. This is a control. This controller, by the way, could be what? Could be a P controller, or it could be a what? A PI controller, or it could be a PD controller, or it could be a combination of proportional integrator and differentiator control. Clear? Now, so at the beginning, what am I going to assume? I'm going to assume that this is what? G of S. Now, we know when you do have two systems in cascade, the overall transfer function is the transfer function of the first subsystem multiplied by the transfer function of the second system. Clear so far? Clear so far? No response. Oh, the frequency response is G of J omega. G of J omega, which is equal to what? G of S with S replaced by what? J omega. With S replaced by J omega. So that's the frequency response. Now, let's look at the Nyquist plot for just a second before we go to the second. In the Nyquist plot, first of all, what do you represent? G of J omega is equal to what? Absolute value of G of J omega times E to the J, the phase angle of E. So E to the J, the phase angle of G of J omega. This is called the what? The magnitude response. Response. This is called the phase response. This is called the phase response. Now, to sketch a Nyquist plot, write G of J omega is the real part of G of J omega plus J times the imaginary part of G of J omega. In other words, write G of J omega in terms of what? In terms of the rectangular representation. This is called the rectangular representation. This is in general, I'll give you an example in just a second. This is in general a function, complex function of omega, write it in terms of what? Real of G of J omega plus J imaginary of J omega. And then sketch a single graph of what? The imaginary part of G of J omega over with respect to what? The real part of G of J omega as what? As omega changes from 0 to infinity. As omega changes from 0 to infinity. Are you following me so far? No response.
Yes.
Are you following me?
Makes sense.
Okay. You don't have to take from minus infinity to 0. The minus infinity to 0 is the mirror image of the 0 to infinity. So you only need to sketch the diagram for omega changes from 0 to infinity. The minus infinity to 0 is the mirror image of what? Of the 0 to infinity. Did you get it?
Yes.
Okay. In exactly the same way as the root locus. In the root locus, remember, we only need to sketch a diagram for what? For one side. The other side, it will be what? A mirror image around the what? Around the horizontal axis. Same idea. Now, where is the magnitude and where is the phase? When you sketch this, let's assume the sketch look like this. Just an example. This is just an example. This is at omega equal to what? 0. You need to what? Increase omega. You are going to go this way. In other words, omega equal to 1, omega. By the way, how many values of omega do we have?
From 0 to infinity, it's infinitely many.
Infinitely uncountable. Now, I am not suggesting that you take what? infinite number of what? Infinite number of omega. You are going to generate these curves using MATLAB anyway. I'm just showing it to you how to do it graphically, because in the final exam, I might ask you to do graphically and verify via MATLAB. You follow me on that? Now, at any point, for example, reaches here, if you sketch a vector like this is the magnitude of G of J omega, and this is the phase angle of G of J omega. Are you following me so far? Or response. Are you following me so far?
Yes.
Yes.
Well, what is the magnitude of G of J omega? What do I do? Can you tell me how do I get? This is the Cartesian coordinates. If I want to get the magnitude, what is it? It's the real square.
Yeah, plus the imaginary square.
Plus the imaginary square, the whole thing what? Square root. Where is the real? At this point, where is the real part? The real part is this one, from here to here. Are you following me?
Yes.
And the imaginary part from here to here. So if you sketch a vector, the magnitude of this vector is the magnitude of G of J omega. Clear?
Clear.
The magnitude, one more time, the magnitude of G of J omega is equal to what? The real part square plus the imaginary part square, the whole thing what? Square root, which is what? Which is the length of the vector from a certain value of omega all the way to the what? To the origin. Notice that as omega increases, will the magnitude change? Notice one. As omega increases, as omega goes here, remember, as you move around the Nyquist plot, what will happen? Omega is changing. Did you get it?
Yes.
Yes.
So let's assume omega came here. What is the magnitude? The magnitude is the length of the vector from the origin to this point. Is it the same as this one?
No, smaller.
No, it's not the same. It's a different one. Will the angle change?
Yeah.
Well, the angle also will change. So, for example, one more time, let's sketch a vector here. What is the magnitude now? This is the magnitude. And what is the phase? This is the phase angle. Did you get it?
Yes.
If you keep changing omega, for example, here, omega is what, 10, 15, 20, and so on and so forth, until you reach what? Until you reach infinity. And then take the mirror image of the graph around the what? Around the horizontal axis. Around the horizontal axis to get the case when omega changes from minus infinity to what? To 0. Did you get it?
Yes.
Okay. And what is the phase angle? G of J omega is what? Tan inverse the imaginary over the what? Over the real. Imagine of G of J omega over the what? The real of G of J omega. Where is it? Show it to me graphically. Let's take this point. Let's take this point. What is tan inverse? Where is the imaginary part? This is the imaginary part. And this is the what? The real part. Tan inverse the imaginary over the real is the phase angle. Did you get it?
Yes.
Oh, this is the what? The Nyquist plot. Now, what is the purpose of the Nyquist plot? The purpose of the Nyquist plot is that it will give us an idea about the stability of the system and the relative stability, which means what? It means the phase margin, the gain margin, and so on and so forth. In exactly the same way as root focus was able to tell us whether there are what, whether the root focus will intercept with the J omega axis, so that we make sure that the K, which is the gain, does not exceed that value. Otherwise, the roots will go to the right hand side of the S plane. Did you get it?
Yes. Makes sense.
Yeah. Now, before we get into the exam, I'm going to go back to the what? To the Baudelaire plot. Now, in the Baudelaire plot, by the way, both of these scientists, Nyquist and Baudelaire, they were, they are American scientists. Clear? They are American scientists, which this we are talking about what? We are talking about in the 30s or 40s. Clear? So long time ago, before you were born. Clear? Here we sketch two separate plots. And here one more time. How many plots did we sketch in the Nyquist plot? How many plots? How many plots did I sketch?
It's just one. It's just one, right?
One plot.
Yeah.
I reform just one plot. In Baudelaire, I need to sketch what? Two separate plots. The first one is 20 log absolute value of J omega, which is the magnitude. This is the magnitude in dB versus what? Log of omega, which means what? I'm going to use what? I'm going to use a logarithmic scale for omega. So when you look at the horizontal axis for omega, what would you see? You see, for example, 0.1, 1, 10, 100, 1,000, and so on. So logarithmic scale. And the second Baudelaire plot is the phase angle of what? G of J omega versus what? Log of omega. Log of omega. So the phase angle is not in dB. The phase angle is either in what? In degrees or in radians. Either in degrees or in a radian. Did you get it?
Yeah.
Yes.
These two plots, the Baudelaire plots and the Nyquist plot, both of them will give you the same information. Will give you the same information. Now, in my opinion, this one is easier, but I will show you both so that you understand what we are talking. Clear?
Yes.
So let's see if you can help me with a simple example. Let's start first of all with the Nyquist plot. The Nyquist plot. First of all, let's identify the important point. Identify the important point. The first one, for example, intersection of the Nyquist plot with the real axis and second point intersection of the Nyquist plot with a circle centered at the origin with the radius one, with the radius one. By the way, when I say centered at the origin with the radius one, i.e., when the magnitude of G of J omega is equal to what? 1. Clear?
Yes.
Clear. Yeah.
And what does this mean? I.e., when the phase angle of G of J omega equal to what? Minus 180 degrees. Did you get it?
Yes.
No. And the third important one, determining how many times if any, and in which direction if any, which direction will the Nyquist plot encircles the point -1, 0. -1, 0. Where is this point, by the way? Where is this point here? Can you show me where is this point? -1, 0
On the left-hand side.
on the left-hand side here, which is what? -1, what? 0.
Yeah.
So in this example, it's just an example. Does the Nyquist plot encircles -1 and 0?
No.
No, it does not. In some other cases, it does. So an important point is what? Important point is to figure out whether the Nyquist plot is encircling the points -1 and 0. And if it is encircling, how many times it is encircling it, and which direction? Is it a clockwise or is it what? Counterclockwise. Did you get it?
Yes.
Yes.
Now, all of these things, by the way, this point here, this one will determine the gain margin, which I will define it to you in just a second. This will determine the phase margin. Again, we will define the phase margin in just a second. And this one will determine the stability of our closed loop system. Did you get it? No response. Did you get it?
Yes.
No. Let's take a simple example. Suppose G of S is equal to 1 over S plus 2. This is a transfer function of what? of the combination of the controller and the what? And the plan. But wait, is it possible we don't use a controller? Possible or not possible?
Possible.
Which means of S is the plan. But if you use a controller, is it possible it's only proportional?
Yes.
Which means what? This will be K. So the G of S will be what? K times what? GP of S. Again, is it possible that it will be PI? Yes, which means G of S will be what? The transfer function of the controller times the transfer function of the plan, and so on and so on, for everything. Clear?
Yes.
Oh, good. Now, what is the first step? So the question tells you what? Sketch D. Now, what's the plot? And determine whether the system is stable or not. Clear so far?
Yes.
I'm still awake. What do I do? G of J omega equal to what? 1 over 2 plus J omega. What did I do? I replaced what? I replaced the S by what? By J omega. Did you get it?
Yes.
Oh, then what? Absolute value of J omega is what? 1 over square root of 4 plus omega squared. Are you following me so far?
Yes.
Or are you following me so far?
Yes.
No. What is the phase angle of G of J omega? It's what? Minus tan inverse of omega over what? 2.
2.
Did you get it? Where is the minus coming from? Because
In the
it's a ratio.
denominator.
It's the phase of the numerator, which is 0, minus the phase of the denominator, which is what? Minus tan inverse of omega over 2. Did you get it?
Yes.
Good. Now, how do I write this in a Cartesian form? In a Cartesian form, what do I need to do? I need to multiply 2 minus J omega over what? 2 minus J omega. Did you get it?
Yes.
Yeah, I
Which
see.
is what? G of J omega equals 2 minus J omega over what? 4 plus omega squared. Did you get it?
Yes.
When you multiply 2 plus J omega times 2 minus J omega, the middle term will cancel. You get what? 2 times 2, 4. And J omega times minus J omega is plus omega squared. So what is the real part? The real part is 2 over 4 plus omega squared minus J omega over 4 plus omega squared. Did you get it?
Yes.
No.
Okay.
This is the real part of what? G of J omega. This, by the way, I'm going to change this into plus and put a minus sign here. Did you get it?
Yes.
This, including the minus sign, is what? Is the imaginary part of G of J omega. You follow me?
Yes.
No. Then what do I do? This is the real part of what? G of J omega. This, no absolute value. This is the imaginary part of G of J omega. Clear so far.
Mm-hmm.
Start at omega equal to 0. Can you tell me what is the real part? Omega equal to 0. What is the real part?
Half.
Half. You put here. What is the imaginary part? Omega equal to 0.
Yeah.
Which is this one. So this is what? 1/2, comma what? 0, which corresponds to what? Omega equal to what? 0. Did you get it? Oh, it's fine. Did you get it?
Yes.
That's not what's like that. Remember, on the curve, one more time, what is going to change? This is the curve. What is going to change as you move along the curve? What is going to change is what? Omega. And at any omega, the length of the vector to the origin is the magnitude, and the phase angle that the vector makes with the positive real axis is the phase. Did you get it?
Yes.
So where is the vector here? At omega equal to 0. Can you show it? Where
It's
is
on the real
To the
axis.
right.
Oh, it's from here to here. How long?
1/2.
Which is what? Which is what you get here when you plug in omega equal to what? 0. When you plug omega equal to 0, what are you getting to get?
2.
Omega 1/2, not 2.
1/2.
1/2, which is this one. Did you get it?
Yes.
Okay. What about the phase? Plug in omega equal to 0. What do you get? What is that?
0.
Of 0, 0, which is the point. Did you get it?
Yes.
Now, as you increase omega, can you tell me what will happen? As you increase omega. Now, first of all, let's take the ultimate value of omega. What is it? Infinity. Yes?
Yes.
Now, where will it be? What is the real part?
Go to 0.
Both of them are 0, which means what? This is the end. This is the beginning. Now, the question is what? How it is going to move? Will it move down or will it move up? So let's see. The real part, is it always positive? Look at the real part. For omega goes from 0 to infinity. Is it always positive? Oh, this one.
Yes, it is.
Huh?
Yes.
This
It's always
is the real
positive.
part. This is the real part. As omega goes from 0 to infinity, will this part be negative or always positive?
Always positive.
Which means what? We are not going to go here.
Yeah.
Did you get it or not?
Yes.
Because this is the negative real part. There is no negative real part here. The real part is always positive. So I'm not getting this. Damn COVID. One more time. One more time. Do you see the real part? What is it? 2/4 plus omega squared. Yes?
Mm-hmm.
Omega equal to 0. What is it?
1/2.
Huh?
Half.
1/2.
What? Omega equal to 1.
2/5.
Omega equal to 2.
1/3.
Well, my point is the following. Will the real part becomes negative or always positive?
Always positive.
Always positive, which means what? This curve, when it goes from omega equal to 0 to omega equal to infinity, will never get to this side. Did you get it?
Yes.
Did you get it?
Yes. Yes. Makes sense. Makes sense.
Now, imagine it. Tell me, is it positive or negative?
It's always negative.
Always negative. For what? For omega from 0 to yes?
Yeah. From omega, from 0 to infinity, it's always negative.
And what about from negative infinity to 0?
Then it's always positive.
Always positive. As the mirror image. So what does it do? It is the what?
Clockwise.
Get it? Get it or not? Get it or not?
Yes.
No. One more time. What is omega here? What is omega here? Follow me so far.
Yes.
Follow me so far.
Yes.
At omega, let's take an example. At omega equals 1, where are we?
1 over square root of 5.
No, it's the magnitude. I'm talking about omega. Where are we at omega equals 1? We are
Oh.
somewhere in it. Did you get it?
Yes.
Oh, what is the length of this vector? Can you tell me what is the length of this vector? This is omega equal to 1. What is the length of this vector?
1 over square root of 5.
1 over square root of 5. What is the base angle? What is this angle here?
Minus the inverse tangent of 1/2.
1/2, whatever that is. So get your calculator and see what is tan inverse of 1/2 and multiply it. This is the base. Did you get it?
Yes.
Oh, what if omega equal to 2? Where are we? Omega equal to 2. Where are we?
5 over 4.
Here. Yes?
Yes.
What is the magnitude? But it's this vector. What is the length of this vector?
1 over square root of 8.
1 over square root of 8, which is lower or higher?
It's lower.
Lower. As I increase omega, what will happen? The magnitude becomes what? Lower and lower until what? Until reach omega equal to infinity. What is the magnitude?
0.
0. Did you get it or not?
Yes.
Now, where is the point of interest? Point of interest is that. Did you get it?
Yes.
Well, it's in circle.
No.
Never.
It will not in circle. So, what do I say? The 9 was 5. That's not circle. what does that mean? When I say it does not encircle the point -1 to 0. Oh, sorry, -1. So that next, let's look at what? Nyquist right here. That number of poles. Number of poles. Transfer function on the right hand side of the S plane. Follow me so far?
Yes.
So what is in our example? Let's look at it one more time. In our example, where is the pole?
-2.
Is it on the right hand side of the S plane?
No.
So what did I say? In our example, equal to what? Here. Did you get it?
Yes.
Oh, so I know P. So I know P here. This P.
Yes.
I know it. I know it. Because what you will give you what is the operable transfer. Did you get it or not?
Yes.
That's right here. P, no. Follow me so far. Are you following me so far?
Yes. Professor, it's a little hard to hear you. I don't know if your microphone might have moved or something.
This better? Hello?
It's better.
Hello?
Yeah, much better. I can hear you. Yeah, much better. I think.
Hello?
It's better. We can hear you now.
Can you hear me?
Yes. Yes.
Yes.
Okay, good. It's better?
Better, much better.
Yes.
Okay, good.
Much better.
So, do we know P?
Yes.
We know P. Now, that C being the number of zeros of the characteristic polynomial. The number of zeros of the characteristic polynomial. What is the characteristic polynomial? 1 plus k g of s equal to what? 0. Are you following me? Walk me
Yes.
here. Oh, recall. H of S, which is the what? The closed loop. I don't know what did we designate this in the class, G of S or H of S. Forgot. Closed loop transfer function. Now remember, it's unity feedback. It's what? G of S, 1 plus G of S. Did you get it? Or respond. Did you get it?
Yes.
Yes.
Okay. So the zeros of the characteristic polynomial are the what? The poles are the poles of what? The closed loop
Your closed loop transfer function.
transfer function. Are you following me?
Yes.
Or respond. Are you following me?
Yes. Yes.
Do I know it? That's here. Let's see. Be the number, zeros of the characteristic polynomial located on the right-hand side of the S-plane. Located on the right-hand side of the S-plane. Are you following me on that?
Yes. Following. That
Do
makes
I
sense.
know it? Do I know Z?
No.
Why? Why I don't know Z? Because it's a function of what? The roots of this
Function of K.
polynomial. The roots of this polynomial are going to change as you change what? As you change K. Did you get it?
Yes.
Yes.
I don't know the Z. I'm trying to figure out what Z is. Z is the number of zeros of the characteristic polynomial, which are what? Which are the poles of the transfer function, closed loop transfer function, that happens to be located on the what? On the right-hand side of the S-plane. Did you get it?
Yes.
That N be the number of clockwise encirclement the number of clockwise encirclement of the point -1 and 0. Are you following me?
Yes.
Do I know it? Do I know what N is?
No.
Why
No.
not? Once you sketch the Nyquist
But
plot,
once you've sketched it, yes. Yeah.
once you sketch the Nyquist plot, you will be able to find N.
Correct. Yeah.
You get it?
Yes. Yes. Yes.
Then P is equal to what? P plus N. This is the what? The Nyquist criteria. Now, caution here. In the book or somewhere else, if you are reading, you might see this one is negative. But if this one is negative, then N is the number of counterclockwise encirclement. Oh, sorry. Let me write it down. Or C equal to what? P minus N. This N is the number of what? Counterclockwise encirclement. You follow me so far or not?
Makes sense, yeah.
Okay, so don't get confused. C equal to what? P plus N. This is the Nyquist criteria. N is the number of clockwise encirclement of the point minus 1, 0. Or Z, this is equivalent to this. But here N is the number of what? Counterclockwise encirclement. Did you get it or not?
Yeah, it makes sense. So I guess you depending on which way you encircle based on your graph.
That is correct.
Yeah.
That is correct. Which one to use? For example, back to our example. What is it? What is N in our example?
Well, it's 0.
0. Why? It never encircled the point. Did you get it or not? Now, in a minute, I will give you an example in which it will. So, but I started with something simple so that you understand how do you sketch the Nyquist plot. Did you get it?
Yes.
Everyone?
Yes.
Oh, good. Now, this system is stable if Z is equal to 0. If and only if. Did you understand it?
Yes.
Why? Why? Let's look at what Z is. What is Z? Z is the number of zeros of the characteristic polynomial, which are the roots of the characteristic polynomial. Yes?
Yes.
So if I tell you there are no zeros on the right-hand side of the S-plane, what does that tell you? It tells you there are, remember, the zeros of the characteristic polynomial are the poles of the what? Of the closed loop transfer function. Are you following me so far on that?
Yes.
Yes or no?
Definitely yes.
Okay. One more time. You are struggling. What are the zeros? What does Z mean? This is the number of zeros. No, zeros means what? The roots. The roots. One is this one equal to 0. That's the zeros of the characteristic polynomial. But because the characteristic polynomial is in the denominator of the what? Of the closed loop transfer function, the roots of 1 plus G of S are actually the what?
The zeros of the characteristic polynomial
Are what?
are those are the poles of the closed loop transfer function.
And I don't want them to be on the right-hand side.
Correct.
I don't want them to be on the right-hand side. So if I get Z equal to 0, then the system is what? Stable. Are you
Yes.
following me or not? And we don't talk about what? Gain margin or what? Phase margin. The system is stable. Did you get it or not?
Yeah.
Which means what? It means any disturbances in the system is not going to push the system into what? Into, first of all, oscillation, and eventually what? The system being unstable. It's always stable. Did you get it or not?
Yeah, makes sense.
Everyone? Everyone? Oh, good. One more time before I give you another example. Do we know P?
Yes,
Do
it's
we know
provided
P?
to us.
Huh?
It's provided to us.
It's provided to us. Why? Because it's the number of poles of the what? Of the upper loop. I know what P is. Do I know N?
Once you've plotted the Nyquist plot, yes.
Once I plot the Nyquist plot, I know what N is. And from these two, I will figure out what Z is. And if Z equal to 0, the system is what? The system is what?
Stable.
Stable.
Stable. Did you get it?
Yes.
Okay. Now let's take another example so that you understand, so that I introduce you the concept of the phase margin and the gain margin. Another example. G of S is K O S S plus 3 S plus 5. What is this? That's the what? That's the upper loop transfer function. Which includes what? What does it include? It includes the combination of C of S times what? GP of S. This whole thing. I called it what? G of S. No response. Clear?
Okay.
Okay. Now, and the question tell you what is a sketch. The Nyquist plot and determine the conditions of stability. Are you following me so far?
Yes.
Oh, I'm waiting. What do I do first? Salute. G of J omega is K of J omega. J omega plus 3 J omega plus 5. Are you following me or not? I replace every S by what? I replace every S by what?
J omega.
J omega. Now, then assume K equal to 1. Are you following me or not? Assume K equal to 1 so that you don't have to worry about the K all the time. In other words, sketch the Nyquist plot for K equal to 1, but if K is more than 1, you are only going to what? To scale your plot. Not sure, did you get my point?
It makes sense.
Huh?
It makes sense, yeah.
Okay, one more time. Let's assume I tell you what? K equal to 1 here. Just an example. If I tell you K equal to 2, what are you going to do with the circle?
You're going to increase the diameter, but leave it touching the...
What I'm saying is that, will this point change?
No.
Why? Because it's 0. So 0 multiplied by any K is still 0. Did you get it or not?
Yes.
Okay. Only this one will become what? Bigger. Did you get it?
Yes.
Okay, let's assume k is equal to 2. Where would this point be? K equal to 2.
It would be at 1,
It will
comma
be
0.
1, comma 0. But will this one change?
No.
Why? Because it's 0. When you multiply 0 by anything, you get what? You get 0. Did you get it?
Yes.
So let's assume k equal to what? 1. Clear? Oh, right? G of j omega is as what? The real value of G of j omega plus j, the imaginary value of j omega. Are you following me?
Imaginary of G of j omega, right?
Sorry, imaginary of G. I'm sorry, G of j omega. Are you following me? Yes or no?
Yes, following.
How? How? I multiply and divide by the conjugate of this.
Right.
Did you get it? In other words, this k over what? J omega minus, plus j omega. J omega plus 3, j omega plus 5, and I multiply it by what? Minus j omega minus j omega plus 3 minus j omega plus 5. Are you following me?
Yes.
Divided by what? Minus j omega plus 3 minus j omega plus 5. You cannot see this? This is minus
No, it
j
makes sense.
omega plus 5. Did you follow me?
Yes.
Okay. Which means what? I multiplied and divided by the conjugate. Which means what? I multiplied and divided by 1. No change. Did you get it? Did you get it?
Yes, got it.
Okay. K equal to what? K equal to 1. So if you simplify this, this is what you are going to get. Minus 8 omega squared minus j 15 omega minus omega cubed over what? 64 omega to the 4 plus omega squared 15 minus omega squared, the whole thing what? Square. Did you get it?
Yes.
Did you get it?
Yep, makes sense.
You want me to show you this? I don't mind.
Algebra, yeah.
Just algebra. Multiplying this by all of these. This is what you get. So where is the real part? The real part is what?
8 omega
The real
squared,
part
or minus 8 omega squared.
is minus 8 omega squared over what? 64
64 omega to the 4.
plus omega squared 15 minus omega squared. Yes?
Yes.
And what is the imaginary part? Still waiting. Minus 50 omega minus omega cubed or 64 omega to the 4 plus omega squared 15 minus omega squared.
Yeah.
Did you get it? Respond. Did you get it?
Yes. Yeah, makes sense.
You get it? Huh?
Makes sense. Makes sense.
Oh, now, help me now. I'm going to sketch. This is the what? The real part. G. J omega. This is the imaginary part of G of J omega. How does this one look like?
I guess start with omega equal to 0.
Where?
Um,
At omega equal to 0. Where? Let's look at the real part. What is the real part? At omega equal to 0.
are you at infinite or negative infinity?
Why? Why? Because we have what? 0 over 0. Did you follow me on that?
Mm-hmm.
At omega equal to 0, what is the numerator?
0.
What is the denominator?
0.
Also 0. So 0 over 0, undefined. I need to use the Hopital's
I
rule.
see.
Did you get it?
Right.
When
Yes,
you
makes
use
sense.
the Hopital rule, what is it equal to?
Negative or 0 over.
Remember, the numerator is omega squared, but the denominator is omega to the fourth, which means what? It means that if you cancel omega square, omega to the fourth, what will happen? You will still have omega square in the denominator. Yes?
Yeah.
So when you put omega equal to 0, what would you get?
You eventually get infinity still.
Plus
right?
infinity or minus infinity?
Minus.
Minus infinity.
Yeah.
Did you get it or not?
Yes.
For both of them.
Yeah.
For both of them, the imaginary and the real part.
Mm-hmm.
Do you agree?
Yeah.
Why? Why both of them?
You have the same problem with the imaginary part, right?
Yeah, not negative. Clear?
Yeah.
So where am I going to get? The curve will start from here somewhere.
Bottom left corner, yeah.
What is that? That's infinity. Minus infinity. Did you get it or not?
Yeah.
No response. Did you get it or not?
Yes.
Okay, good. Now, I want you to look at the imaginary part. When does the Nyquist intersect with the real axis? With this real axis?
Mm-hmm.
When the Nyquist plot, the imaginary part of the Nyquist plot will intersect the real axis at omega equal square root of 15.
Yeah.
Did you understand where the omega equal square root of 15 came from?
It's 15 times omega minus omega cubed, so it would have to be.
Will be equal to
15,
what?
yeah.
Will be equal to 0. Did you get it?
Yeah.
So how do I have? Follow me. One more time. What is omega? Here.
Is that at 0? That's off at infinity.
0. This is omega equal to what? 0. What am I doing? I am increasing omega. Did you get it or not?
Mm-hmm. Mm-hmm.
When I reach here, what is omega?
Omega equal to square root 15.
Continue. I keep increasing omega. Can you tell me what is this?
Infinity.
Why? Can you show me why it is
The
infinity?
same reason as before. Like you'd need to use L'Hopital.
Oh, I
And
use the
then-
Hospital's rule, and I get 1 over infinity, which is how much? 0.
Here.
This is omega equal to what? Infinite. Did you
Mhm.
get it?
Mhm.
Now, on the negative side, what does the curve look like? On the net, when omega is negative, remember, omega is negative is the mirror image.
Yeah.
So what is
So
it?
it
Let's see.
loops down and then goes up. Yep.
Yes? What is this? Where are we headed to here? Here. Where are we headed?
To what is
0
it?
minus. This one, it's 0 plus.
Oh,
Did you
sure.
get it?
Right. Yeah.
Are you following me so far on that?
Mhm.
This is an aqueous plot. Now, when you do the MATLAB, you will get something this one and you will get something here. But I don't care about this. Did you get it?
Yeah.
No response. Did you get it?
Yes.
Okay. Now, please listen. Where is the point -1 and 0?
-1. Well,
The
we
point.
haven't done like a scale yet, but it's somewhere on the left-hand side.
No, we don't know yet. So
We don't know
let's
yet.
understand how we get it. When when the imaginary part equal to 0, when the imaginary part equal to 0, what did we find? Omega equal to what? Square root of 15. Did you get it?
Yes.
What do I do with this? I take this and I substitute it in the real part. Did you get it or not? To find what is the real part of this point.
Yes. Makes sense. Makes sense.
Did you lose me?
No. That makes perfect
So,
sense. You're just finding the intersection.
Yeah. Substitute omega equal to what? Square root of 15 in the real part of what? G of J omega. Where is the real part? This part. Did you get it?
Yes.
This one. You plug in omega equal to what? Square root of 15. You follow me or not? You will get this one.
Right.
Clear? Oh, sorry, minus. Sorry, minus. No response. Did you get it?
Yes.
Okay, where is it here? Can you show it to me? Where is this one here?
That's the intersection point with the real axis.
Which is this one, with the real axis. So
Uh-huh.
where is the -1 and 0? Minus
Way
1
up
and
the side.
0 is here.
Uh-huh.
Are you following me
Yep.
or not?
Yep.
So listen to my statement. If K equal to 1, the system is stable.
Yes.
Okay, first of all, let's see if you got my point very clear. Okay, first of all, what is P? I'm still waiting. What is P?
The number of right-hand side poles of the open loop transfer function.
Very good. Is the number of poles of the open loop transfer function which are on the right-hand side of the S-plane.
Mm-hmm.
Clear so far?
Mm-hmm.
How much? In our
Um,
example, where is
hmm.
the example?
Oh,
One more time. Where is the example? This one.
yeah.
Do we have any poles on the right-hand side of the x-plane?
No.
No. So B equal to what? C.
0.
Did you follow me?
Yes.
Now, for K equal to what? 1. What is N? Which is what? What is the N? Is the
Number
number
of
of
clockwise encirclements.
clockwise encirclement the number of clockwise encirclement of the point -1 and 0. No response. No response. How much?
0.
0. What does that mean?
It means that the system is
Z
or the closed loop
equal
transfer function
to Z.
is stable.
Remember, Z equal to what? P minus what? P minus what? Sorry, plus what?
Hmm.
N. And remember, N is the number of what? Clockwise. So N is equal to 0. P equal to 0. What is Z?
0.
Which
0.
means what? What does that mean? It means there are no poles, i.e., the closed loop transfer function has no poles on the right-hand side of the S-plane. Did you get it?
Makes sense. Yes.
And then what conclusion? System is what?
Stable. For all value, or no, not for all values. At k equal to 1.
At k equal to 1. At k equal to 1. Did you get it?
Yes.
Now, will it remain stable as I increase k? As I
No.
increase
No.
k, will it remain stable or not?
At some point, it will become unstable.
Why? Because what did I tell you a moment ago?
We're
As
gonna
you
scale.
multiply by k, you are scaling. What is the point here? What did we find here? We found it to be equal to what? 0.0083. Did you get it? This point here, 0.0083. If you scale it by k, eventually the point will go where? Here. Did you get it or not?
Yes. Makes sense. Makes sense.
When
K is equal to 1 over 0.0083,
so
which
what do
is
I
1.
say?
Yeah.
Let's see if you can help me. When k equals 1.0083. Are you following me so far or not?
Yeah.
Where is the paper? Here. But wait, don't put the minus sign. Why? Because we are only interested in positive k. We are only interested in positive k. Clear?
Yeah.
And that equal to what? 1 approximately 120 approximately. Yes?
Mm-hmm.
The intersection of the Nyquist plot with the real axis becomes what? You follow me so far or not?
Yes, following.
You lost me here. Did you lose
Yes,
me?
yes.
This point. This point. Now, why for this example, this point did not change? This point in the first example, why didn't it change?
It's already at 0. So if you
It's
multiply
already
it,
at 0.
yeah.
So no matter what you multiply it, it will still be what? 0.
0.
But in here, is this 0?
No.
So when you scale it, it will become what? Bigger and bigger and in the negative. Why it is in the negative? Because it's what? It's minus
already in the negative.
0.0083. It's already negative.
Yeah.
Did you get it?
Yeah.
This is referred to as the what? The gain margin. And what do I say? Now, this one is specified in what? dB, which means what? You need to take 20 log 120. I don't have a calculator with me. What happened to my calculator? Does anybody have a calculator?
I can do it.
Tell me, huh? No
I got it. 20 times log 120. 41.6.
41.6 dB. Before the system becomes marginally stable, and soon after unstable. Did you get it?
Yep.
No response. Did you get it?
Yes.
Clear? No response. Clear? Can
Yes.
you hear me?
Sure. Yes.
Yep. Yep.
Can you hear me?
Yes.
Yeah. Yes.
Okay. So, in other words, if there are disturbances in the system that results in increased gain, the system will still tolerate it. Provided what? Provided that the gain does not exceed what? 120. So what do I say? System is stable or okay, between 0 and 120. Okay, don't put the equal sign here, by the way. Don't put the equal sign here. Well, once you put the equal sign here, it means the system is what? Marginally stable. I don't want it marginally stable. Say something. Did you get it?
Yes.
Everyone? Everyone? I'm not sure you can hear me. Some of you cannot hear
Yeah.
me. Everybody can hear me?
Yes, we can hear you. We can hear you.
Okay. Omega PC, which is called the what? The phase crossover frequency is the square root of 15 radian per second. Now, what does phase cross over mean? What does phase cross over mean?
That's the point at which you cross
phase.
the real axis?
One second. The phase cross over frequency, which is what? Omega P C is when the phase angle crosses minus 180 degree. You lost it. Did you lose it? Yes.
Makes sense. Makes sense.
Yes, you did. One second.
Okay.
One second. Yeah. Remember, by the way, the magnitude, how would you sketch the magnitude for any omega? For any omega, let's assume I take this omega. How do I get the magnitude? This is the magnitude. Yes? No response. Yes?
Yes.
And what is the phase? This is the phase.
Mm-hmm.
Did you get it or not?
Mm-hmm.
Now, when I get here, can you tell me what is the magnitude? When I get here at the point where it is intercepting the real axis, what is the magnitude?
0.0083.
Yeah, don't put minus sign. The magnitude is always positive. Did you get it?
Right. Yes.
What is the phase angle? What is the
Minus
phase
180.
angle? Minus 180. Agree?
Mm-hmm.
Increase omega. Increase beyond square root of 15. Can you tell me what is the magnitude and what is the phase? Let's assume I'm here right now. Here. Remember, what is this? This is omega equal to what?
Zero.
Infinity.
Or infinity, sorry.
So as I move along this axis, I am increasing omega from where? 0 plus all the way to what? Infinity. The point where it intercepts with the real axis is the square root of 15.
Yeah.
Give me a value more than square root of 15. More than square root of 15. Let's say 20.
Sure.
Sorry, let's assume 5. Are you following
Sure.
me or not?
Yes.
Where is it? Can you show me this point where omega equal to 5? Where is it? Here,
The top half of that little circle, yeah.
in the top half. What is the magnitude? You sketch a what? From the origin to that point, that is the magnitude. Yes?
Mm-hmm.
What is the phase? Remember, the phase measured from here. So what is the phase? Is below minus 180. Because at this point, what is the phase?
Minus 180.
So as you move up, what does it become? Less than minus 180.
Yeah.
Let's
Less
say,
than,
for
yeah.
example, minus 200. Did you get it or not?
Yes.
No response. Did you get it or not?
Yes.
Which means the phase across the what? The minus 180 degree. Clear? No response. Clear? No, you didn't get this one. Did you get this one? Didn't get this. Okay. Okay. Let's go back to our first example. At omega equal to 1, what is the phase? This is the phase. Yes?
Mm-hmm.
At
Mhm.
omega equal to 2, what is the phase?
Yep.
Are you following me or not?
Mm-hmm.
All the way to what? Omega equal to what? Infinity.
Yeah.
Yes?
Mm-hmm.
What is the phase?
0?
No. Remember, you are moving this way. The phase here is 0.
Yeah.
You are not getting it. One more time. What is the phase at this point?
0 for sure.
What is the phase here? Give me a number. Give me just a number.
Minus 20, whatever, yeah.
Let's say minus 20. Yes?
Mm-hmm.
Okay. What is the phase here?
Minus 30.
Minus 40. Minus 50. Minus all the way until what? Minus 90. Why? Because you are what?
Oh, I see.
You are headed this way.
Right.
Did you get it?
Yeah, that makes sense.
Yeah. By the way, will it ever get to minus 180?
Mm.
Here. Will it ever get to minus 180?
Mm.
No response.
No.
Why not? Correct. We'll never get to minus 180. Why not? Look at the phase angle. Oh
It never goes to the left-hand side.
Look at the phase angle one more time. At omega equal to 0, what is it? What is the phase angle at omega equal to 0? What is the phase angle? No,
0.
G. At omega equal to infinity, what is it?
Minus 90.
Which means what? Will it ever get to minus 180?
No, never.
No, it will never get to minus 180. This is a single pole, first order system. Did you get it or not?
Yes.
Oh, now let's go to the second example. What is the phase, by the way? What is the phase? Which page? Can you tell me what is the phase? Phase of G of J omega. I'm still waiting. What is the phase of the numerator? K is positive, so it's 0. Yes? What is it?
Yeah.
Minus 90 degree. Yes? Minus tan inverse omega over 3. Yes? No response. Yes? No response.
Yes.
Minus tan inverse omega over what? 5. Did you understand where this came from?
Yes.
No, you didn't. Okay. Open bracket. This plus. Can you tell me why? First of all, why do I have a minus?
Because of the denominator. It's in the denominator.
Because of the denominator. What is the phase of this one? Only this term. There is no
always
real
minus
power.
90.
Huh?
Or always 90 or minus 90, I
Always
guess.
90. This 90.
Yeah.
What is the phase of this guy?
That's the inverse tangent of omega over 3. So
What
it's
is the phase angle
imaginary
of this
part.
one?
Inverse tangent of omega over 5.
Why am I adding them?
Because they're all in the denominator.
I know. Why am I adding them? Because they are
The phases,
multiplied.
yeah, when they multiply, the phases add, yeah.
Phase add. And then what? The negative is because the numerator, the phase angle is 0. Did you get it?
Yes.
Now plug number. Plug omega equal to 0. What do you get? Plug omega equal to 0. What is the phase? Plug omega equal
minus
to 0.
90.
Where? Show it to me in the graph.
All the way down at the bottom.
All the way here. Minus 90. Did you get it?
Yeah.
Now, omega equal to infinity. What is it?
At omega equal to infinity, it's going to be minus
why is this so hard? Plug in omega equal to infinity.
Yeah.
What is tan inverse of infinity?
Minus 270?
Minus 270. Where is it?
Right. Okay. Yeah. Oh, right.
Where is it here? Where is the
That's
minus
at 0,
270?
0.
That's this one. You see, it's becoming this way. Did you get
Yeah,
it?
right at 0, 0.
At 0, 0. Yes or no?
Yes, makes sense.
So what is the phase here at this point?
Minus 180, right?
Oh, that is why they call it the phase crossover frequency, which is what?
Yes. Okay.
Which is the frequency at which the phase angle will be what? Minus 180.
Mhm.
Did you get it?
Yes, makes sense. Okay.
Everybody in the class? Everybody in the class? I don't know what.
Yes.
Yes.
Here,
Yeah.
I'll plug in. Plug in. By the way, listen to me. Can you plug in omega equal to square root of 15? Here, and
Yeah.
use your calculator. Give me what is this angle. This omega. Do you see this omega? Can you plug in square root of 15? And tell me what would you get? By the way, the angle is in degree.
Tangent of square root 15 divided by 3.
And not tangent, tan inverse.
52.2
Okay.
for
And this one.
that one is 37.7.
Add them. And add with 90 with. So 90 plus whatever, 52 plus whatever, 37. What would you get?
I get 180 or minus 180, right?
Minus 180. Did you get it?
Yeah.
That's this way. At this point. That point, omega, that is called what? The phase crossover frequency. Not the gain. The phase crossover frequency. Did you get it or not?
Yes, makes sense.
Which is what? Which is the value of omega in which the phase will hit minus 180.
Yeah.
And if you increase omega beyond this omega, beyond square root of 15, the phase angle will become what? Lower than minus 180. Lower means what? More negative. Right. Eventually reaching what? Minus 270.
Yeah.
Did you get it?
Yeah.
Why in this example, the phase, we were able to reach minus 270? Why? Because this one has 3 poles. This is a third order system. Whereas in our first example is a first order. With first order, you cannot get a phase angle lower than what? 90 degree. Sorry, minus 90 degree. Did you get it? No response. Did you get it?
Yes. Yeah.
One more time. This example number 1. This example number 1. At omega equal to infinity. What is it?
Which one? The angle, the phase? Oh,
the phase
minus 90.
Can you get any higher than infinity?
No.
Which means what? This is a first order, a single pole. Maximum phase it can give you is what? Minus 90 degrees. 90. Now, why it is minus? Because it's a pole. If it was a 0, then it will become what? Plus 90. But this one is a pole. Did you get it?
Yeah.
No response. Did you get it?
Yes.
So let me ask a question. Suppose I don't have SA. Suppose I don't have S here. What is the maximum phase can you get?
9 or
suppose I don't
minus
have
180.
Minus 180. Why? Because it will become a what? A second order system. It cannot go less than minus 180.
Right.
Did you get it?
Yeah.
No response. Did you get it?
Yeah.
Yes.
So summarize this for me. When you talk about what? The phase crossover frequency, you are dealing with what? With the gain margin. Did you get it? Response. Can you hear me?
Yeah, can you repeat that?
Oh, oh. Concentrate, guys, concentrate. Have mercy on me. When what? When you deal with the gain margin, which frequency do you take? The phase crossover frequency, the phase angle crossover frequency.
Yes.
Do you follow me on that? See, students
Yeah,
always make the mistake when they use what? When they try to find the gain margin, they use what? The gain crossover frequency, which is wrong. You need to use the what? The phase crossover frequency to find the what? The gain margin.
Right.
Did you get it?
That makes sense, yeah. Because you want to know the intersection with the real axis.
That is correct. Now, how do we find the gain crossover? Frequency and the phase margin. Again, do you see what I'm talking about? The gain crossover frequency, which is what? Omega GC. Don't confuse omega GC with what? Omega PC. Did you get it? Oh, now I want you to go back to the diagram. Can you tell me what is the gain here? The gain is what? You sketch a vector from the origin all the way to what? To the point. Where is this point? This point is at infinity, minus infinity, which means what?
Yeah.
What is the gain?
Infinity.
Okay. Now, before we continue, can you tell me how do I get the gain? This is the what? 1 second. What is page? This is the real part, and this is the imaginary part. Can you tell me how do I get the gain? Sorry, how do I get the magnitude?
Square root of the square of the real times the square of the plus the square of the imaginary. Yeah.
And then what? The whole thing
The
square root.
The whole thing. Yeah.
Did you get it?
Yeah.
Oh, at omega equal to 0, what is the magnitude?
Infinity.
As I increase omega, which means what? As I move here, yes, will the magnitude increase or decrease?
Decrease.
Say that again.
Decrease.
Decrease. Are you following me or not? Decrease. Clear? When does it reach 1? When does it reach 1? What do? I sketch the unit what?
Circle.
Circle. Are you following me so far or not?
Yes.
No response. Yes or no?
Yes.
Is this a unit circle?
Yes.
What is the magnitude here? At this omega. What is the magnitude?
1.
Show it to me. Vector. Where is the vector?
From the origin to that point.
from the origin to that point. So here, the magnitude is 1, which corresponds to what dB?
0.
0 dB. Now increase omega. Beyond this omega. Beyond this omega. Does the magnitude increase or decrease?
Decrease.
Which means it becomes what? Less than 1. Which means in dB, it becomes what? Negative dB. Did you get it or not?
Yes.
No response. Did you get it or not?
Yes.
This, the value of omega here, we call it what? Omega gain crossover frequency. So what is omega GC? Omega GC is the what? The frequency at which
gain crossover frequency?
At which this is the gain crossover. Omega, the frequency at which the gain crosses from positive dB to what? Negative dB. Are you following me or not? No response. Are you following me or not? No response. Are you following me or not?
Yes.
Okay. What is it? Which is what? Which is the point? Sorry, it is the frequency at which the Nyquist plot intersect with O. No response. No response.
Intersects with the unit circle.
With the unit circle. Did you get it or not? One more time. What is 20 log 1? I'm still waiting.
0.
0 dB.
Yeah.
Can you tell me what is 20 log? Get your calculator. 1/2. What is it?
Isn't that -3?
-3 dB.
Ooh, clean.
Yes?
Yeah.
Okay. Now, one more time.
Oh, wait, no,
What is-
Professor, it's -6. That's my bad. That's my bad. I did that wrong.
-6 dB. Yes?
Yeah.
Okay. What is log 2? 20 log 2.
That's 6 dB.
6 dB. Where is the 2 here? Where is omega equal to 2 here? Sorry. When is the magnitude 2? Is it here or is it here?
Below.
Below. Why? Because once you reach the unit circle, this
You're only getting
vector
smaller.
is how much?
1.
1, which means what? 0 dB.
Yeah.
Clear? No response. Clear? What is the magnitude at this point? I'm not sure you are hearing me. Can you hear me?
Yes.
Can you hear me?
Yes. Yes.
What is the magnitude here?
1.
What is the magnitude here? Lower than 1
Less than,
or? Huh?
Less than 1. Less than 1.
Which means in dB, is it positive or negative?
Negative dB.
Negative dB. Now do you understand why they call it the gain crossover frequency?
Yes, it's when it goes from positive dB to negative dB.
That's what I wrote here.
Yeah,
It's the
I know.
frequency at which the Nyquist plot intersects with the unit circle, which means what? The frequency at which the gain crosses from what? Positive dB to what? Negative
Yes.
dB. Did you get it?
Yes.
How do I get it? How do I get this frequency? I'm still waiting.
You should create the function for the magnitude.
I need to get the magnitude. So, in other words, get the magnitude. How do we get omega GC? How do we get omega GC, which is the what? The gain crossover frequency. What do you do? Set absolute value of G of J omega equal to 1 and solve for what? Omega, which is what? Equal to what? Get GC. And what is the magnitude? Is real square plus the imaginary square, the whole thing what?
The whole thing square root.
Square root. Now, can you give it to me for our example? You don't have to do this, but just give me the magnitude. One second. Can you give me the magnitude of this? For k equal to 1. Remember, k equal to 1. Can you give me the magnitude? Magnitude of what is it? 1. Oh. What is the magnitude of J omega? What is the magnitude of J?
1. Or sorry,
So
omega.
what is it? Omega. Times what? Square root.
Yeah.
Omega
squared plus 9.
Times what? Square root.
Omega squared plus 25.
Sorry, plus 25. Yes?
Yeah.
Set this one equal to what?
1. Mm.
Did you follow me on that?
Yes.
And find what? Find omega. This omega is what? Omega GC.
Yeah.
Did you get it?
Yep. Yep.
Now, for k equal to 1, what is omega GC compared to omega PC? Which one is larger? I'm still waiting. Where is omega PC, by the way? Where is omega PC? That's
right there, yeah.
This
omega PC, like the phase crossover is larger.
So for k is equal to 1, we already know that the system is what? Stable.
Yeah.
Did you get it?
Yeah.
So omega GC is less than what? Omega PC.
Yeah.
Did you get it?
Mm-hmm.
In general, for this system to be stable, omega GC must be less than what? Omega PC.
Mm.
Are you following me or not?
Yeah.
If omega GC is equal to omega PC, system is marginally stable. Why? Can you tell me why?
You hit that point.
I am hitting this point. Did you
Yeah.
get it or not?
Mm-hmm.
But if omega GC is greater than omega PC, system is what? Unstable. Did you get it or not?
Yeah.
I do not want to do what? I don't want the gain crossover frequency to be greater than the what? Than the phase crossover frequency.
Right.
Did you get it or not? Notice,
Yeah.
by the way, when I say marginally stable, what does it mean? System what?
Will oscillate.
Now, can you show me where is the phase margin?
Where
is the
point
phase
where it
margin?
intersects the real
Now,
axis.
first of all, do you see this one?
Sorry. Yeah.
Do you see this one?
Yeah.
Yes or no?
Yes.
Okay. If you increase K, how are you going to rotate? Remember, as far as the phase is concerned, if you increase K, what will happen? What will happen is that this curve will what? Rotate. Did you get it or not?
Mm-hmm.
Do you see this point?
Mm-hmm.
Where as you increase K, where does it go? Around the what? Unit circle? Because it's a unit again, right?
Mm-hmm. Mm-hmm.
So it move until it hits this point.
Right.
Did you get it or not?
Yeah.
That's how much phase margin do I have from here to here. This is called the what? The phase margin. Which means what? What is the phase margin? The phase margin. You lost me here?
No, makes sense.
Did you lose me?
No.
What is the phase margin? The phase margin is what? 180 degree
Mm-hmm.
minus the phase of what? At what?
Omega GC.
At omega GC. What is the phase at omega GC? Can you tell me what is the phase of omega GC
Like
here?
110.
Let's say 110 or 100 and what? There, 120. Yes? Minus 120. Yes?
Yeah.
How much can I what? How much can I decrease the phase until it reaches 180? It's
50
what?
degrees.
180 minus what? 120, which is what? 60. So in this case, in our example, by the way, I'm assuming this is 120. I don't know if it is 120. How do I know? How do I calculate this? Can you tell me how do I calculate this? How do I calculate the phase? How do I calculate
You
this?
plug in omega GC into
where I plug it? I plug it in the what? In the phase angle, which is this one. Do you see it? Oops, sorry. This one.
Yeah.
Did you understand it or not?
Yeah.
No response.
Yes.
Okay. Let me write it down. Yes, you find it by plugging omega GC in the phase equation, which is what? Phase of J omega equal to what? Minus 90 degrees plus tan inverse omega over 3 plus tan inverse omega over what?
Can you hear me?
Yes.
What is it? Can you hear me?
Yes.
Yes.
Did you get it or not? Oh, sorry.
Yeah.
I messed up. That. Yeah. What is this? Why am I getting this? Yeah, gone. Did you get it?
We can still see, yeah.
Huh?
We can see and hear you still, yeah.
So one more time. How do I get omega GC?
Set the magnitude equal to 1.
Oh, equal to 1. You get omega GC. Yes?
Yep.
Yes?
Yep.
And then what? Plug this omega GC in the phase equation.
Mhm.
In the phase equation, what do you get? You get this one. The phase at what? Omega GC.
Mhm.
Subtracted from 180.
Mhm.
Did you get it or not?
Yes.
You get the phase mark. We get. Clear? No response. Yes.
Yes.
Okay. So can we summarize this before we go to the Bode plot? Can you summarize it for me?
So
Can you summarize it for me?
everything, right?
Everything. I want you to summarize whatever I just mumbled for the last hour. Can
Starting
you
with
summarize it for me? Start, first of
yes.
all, identify P. What is the P? P
Sure.
is
So
the number of poles of the upper loop
mhm.
on the right-hand side of the S plane.
Yes.
Did you get it?
Yes.
Okay. By the way, once we get to the digital, which is this coming Wednesday, what will be? Be the number of what? Poles of the upper loop, which is outside the unit circle.
Mm-hmm.
Did you get it or not? But this is for
Yeah.
the continuous. So we are talking about what? Right-hand side of the S plane.
Right.
Are you following me?
Yes.
Okay. Then what? You are given the transfer function, which is this. Yes?
Mm.
Change every S to what? J omega. Did you get it?
Mm-hmm.
Write it in a Cartesian form, which is what? Real and imaginary.
Mm.
Did you get it?
Yes.
Put the imaginary part equal to what? 0. Are you following me? No response. Are you following me? The
Yes.
imaginary part, put it equal to 0. Yes?
Uh-huh. Yes.
What are you getting? What omega
That's
are you
the
getting?
omega PC, the phase
Omega
crossover.
PC. Are you following me?
Yeah.
Then what do you do with omega PC? Plug it in the real part. Remember, the imaginary part equal to 0. Plug it in the real part of G of J omega. Are you following me?
Yeah.
What do you get? You get the point where the Nyquist plot intercept with the what? With the real axis.
Mm-hmm.
Are you following me?
Yeah.
1 over that is the what? Is the gain margin. But
Yep.
you need to change it to dB. 1 over it. So in our example, what was it? What was it? 0.0083. By the way, this omega is what? This omega is omega PC,
The PC. Yeah.
the phase crossover frequency. What is this?
Mhm.
One more time. This is this interception, the coordinate. Yes? 1 over it, 1 over this is the gain margin.
Yep. Yep.
But you need to write it in dB.
Gotcha.
Yeah. So did we understand the gain margin?
Mm-hmm.
Everyone?
I did.
The rest? I can only hear you voice. The rest, are you hearing me or not?
Yes.
Oh.
Yes.
Yes.
Oh,
Yes.
good. It's killing you to say yes. Is it killing you?
Yes.
Just say yes. What is the problem with that? Okay. So are we done with the gain margin?
Yep.
Now, how do I get the phase margin? Help me step by step. What do I need to find? I need to find the gain crossover frequency.
Mhm.
What do? I take the absolute value. Are you following me?
Yeah.
And what do I set it equal to?
To 1.
I set it equal to what? Equal to 1.
1.
Where did I write it? 1 second. Here. That's the absolute value. I set it equal to what? 1. And what do I calculate? At what omega?
Mhm.
Are you following me or not?
Yeah.
What is that omega? That omega is omega GC, which is the gain crossover frequency. Did you get it?
Yes.
Then what do I do with this omega? I substituted in the what? In the phase
Into
equation.
the phase.
Phase equation. What do I get? I get this phase equation. Sorry, I get this phase. At what omega? At omega GC, which is the gain crossover. Did you get it?
Yep.
If this phase angle is already less than minus 180, give me a value less than minus 180. Let's say minus 400.
Minus 200, sure.
And then you are what? You are hopeless.
Yeah.
In other words, there is no phase margin. Actually, there's a phase deficit. Did you get it?
Yeah.
No response. Did you get it?
Yes.
The angle should be what? Should be more than minus 180. Give me a number more than minus 180.
Minus 110.
Minus 110. What do you say? You say I have a phase margin of 70.
Yeah.
Did you get it?
Yeah.
And the larger the phase margin, the more stable your system is for larger values of K.
Yes.
No response. Did you get it?
Yes.
Response. Did you get it? The larger the phase margin, the larger the what? The gain margin, the larger the phase margin or gain margin or both, the what? The more stable the system is, which means what? I.e., it can
Increase gain further?
it can overcome disturbances
Hmm.
in the system. Disturbances in the system that causes what? That causes changes in the gain, that results in changes in the phase and so on, so phase shift and so on, so phase jitter. What is a jitter? Jitter is the change in the phase. Are you following me or not? No response.
Yeah.
Which means what? It's better. By the way, when you design what? When you design your amplifier, for example, or something like that, you would like the phase margin to be at least 50 degree, 50. there will always be fluctuations in the power supply and so on and so forth. You need a phase margin, which is at least what? At least 50. Clear? Now, the body. One more time before we go to the body. Did you understand the last statement? What is the last statement? 1 second. Where did I? This one. Did you understand this one?
Yeah.
The gain crossover frequency needs to be what? Lower than
Less
the
than.
what? The phase crossover frequency. Otherwise, you are hopeless.
Yeah.
Did you get it or not? No response. Did you get it or not?
Yes.
Okay. Body plots. What do I have? 2 plots rather than what? This is log of omega. And what is this? 20 log the magnitude of G of J omega. Yes or no? No response. Yes or no?
Yes.
That's the magnitude. By the way, you don't need to write the real part and imaginary part, just the magnitude. And another curve, log of omega. This is the phase angle of G of J omega. And one more time, G of J omega, G of J omega. This is the what? This is the upper lobe transfer function. That includes both the controller and the what? And the plant that you are trying to control. Did you get it?
Yeah.
Okay. Now answer me the following question. This is in dB. Let's assume the curve looks like this. Can you tell me what is this omega?
That is the gain crossover frequency.
That's the gain crossover frequency. Did you get it?
Yep.
Okay. Let's see if you can help me. And the phase, let's assume the phase is something like that.
Yeah.
And this, just an example, minus 180. Can you tell me what is this frequency?
Phase crossover frequency.
That is omega P C. Are you following me so far? Help me. In this example, which one is larger? In this example, which one is
The
larger?
phase crossover.
frequency.
Which means what? If the phase crossover frequency is larger than the what? The gain crossover frequency, the system is what? Stable. Can you show me where is the gain margin? Where is the gain margin? What do I do? Follow me. Put a straight line like this until you hit the what? The gain from here to here. This is the gain margin.
Yeah.
Did you get it?
Yeah.
And who decide the gain margin? Omega PC, which is the what? Phase crossover frequency.
Yeah.
Did you get it?
Yeah.
Can you show me the phase margin? Can you show me the phase margin in both their
Do the
plots?
same, but from the gain crossover down.
Down until you get this phase.
Yeah.
This is the what?
Phase margin.
Phase margin. Did you get it?
Yeah.
No response. Did you get it?
Yes.
Oh, now suppose this one appear before this one. In other words, suppose I have this. Where is the phase margin? Sorry, where is the -1? Where is the? I need to sketch the magnitude. Where is the gain crossover frequency? The gain crossover frequency. The gain crossover. This is 0 dB. Where is the gain crossover frequency?
The point where it intersects the, yeah.
Where is the phase crossover frequency?
The point where it hits -180.
That's. Are you following me or not?
Yes.
Okay. Do we have a gain margin? What do I do? How did I get the gain margin? How did I get the gain margin? By the way, which one is larger? Omega GC? Sorry, this one is, I'm sorry. This one is, I'm sorry. This one is Omega PC.
PC, yeah.
Which one is larger? Omega PC
GC.
or Omega GC?
GC is larger.
GC is larger, which means the system is what?
Unstable.
Which means what? There is no margin. But can you show it to me? If you sketch this, this one, yes? No response. Yes? What is it? This is the gain margin, but it's in what? Negative dB. Did you get it or not?
Yeah.
What does that mean?
We're sad.
We are sad. Where is the phase margin? Can you show me the
Do the
phase
same
margin?
thing. Go down from the GC and then
The phase is already below what?
-180.
It's already -180. Where is the phase margin? Which is what? Negative. Did you get it?
Yep.
Double sad. No, sorry. Wrong map. And what are these? What are these? Tears.
Is that a mustache?
We're even more sad.
The more sad. This is tears. Did you
Is
get
that a mustache?
Huh?
Is that a mustache?
Yeah, that's a mustache. My mustache. Now, let me ask you a question. Can I ask you a question? How do I make sure that this point is to the right of this point? What do I need to make this point? Where do I need to make this point?
You need to move it left? Is that, am I understanding?
Left means, 1 second. Left means this side.
Yeah.
Yeah, that is correct. You need to move that. Now, remember, which means what? The slope. Remember, by the way, every pole, you are going to get how much dB? -20 dB per what? Decade. You lost me here. Did you lose me?
Mm-hmm.
Huh?
I don't think so.
You lost me?
I see what you're saying, yeah.
Which means what? I need to reduce. See, the steeper this curve is, what does it mean? It means it will hit what? If you move this one to this side, which means what? This is a pole frequencies because you are, the body plot is going down. So you are putting the pole on here. You should put the poles where? Here, so that this one it drops sooner rather than what? Later.
Yeah.
Did you get it? No response. Did you get it?
Yes, yes.
Now, I ran out of time, but I need to show you one thing for next time. What is going to change for discrete system? What is going to change? Let's see if you can help me here. Okay, what am I going to find first? G of what? C. Are you following me or not?
Yeah.
This is called the what? This is called the pulse
Transfer
transfer
function.
function. Okay, let's see if you remember the system function. Let's see if you remember the system. What do I have? Then what? What is this ideal sampler? Yes. This is what? This is the controller. Are you following me or not?
Yeah.
This is the what? So, yes, this is the what? The analog system, the plant. No response. Did you get it?
Yep.
Okay. Can you tell me what is G of C? Which is the what? Remember, this unit feedback. This whole thing is G of C. What is C of C? Which is the controller? Be careful. Be careful. What do I write here? G Z A S of Z. What does that mean? What is ZAS? Zero order hold
And
plus
system?
analog system. So when I say 0AS, how do I find this? This is what? 1 minus C minus 1 times what? The C transform of what? 1 over S G P of S. Can you tell me where did this come from? I'm still waiting. What is this O? What is this O of S?
1 minus 0 over Z?
ST over what? S.
You're right.
Yes? But what is E to the minus ST?
Z to the minus 1.
So where is this S?
It's inside there.
I need to multiply this by this. Then what do? I take the inverse Laplace transform. Then what do? I sample it. And then what do? I take the Z transform. Did you get it? No response. Did you get it?
Yes.
This is what? This is this one. Only this one. Then I need to multiply by what? C of what? C, which means what? G of Z equal to C of Z times. Did you get it?
Yes.
No response. Did you get it?
Yes.
Now, what is the frequency response then? Oh, the open loop is what?
Same idea as before. You just replace Z with J omega, right?
No, absolutely not. You replace
Okay.
Z by E to the J omega.
Oh, okay. Makes
Did
sense.
you get it? This is the hard part of the discrete. The beauty of the analog is that I just replace S by what? J omega. Did you get it?
Yeah.
Can I squeeze one example?
Sure.
Can I squeeze one example before I let you go? Let's assume G of C yes. No response. Yes. What do I need? That's a frequency response. Notice, by the way, This is periodic with period. With period to pi. What is it? Did you get it or not? I'm going too fast here. Did you get it?
Yes. No, I see it. You're going fast, but it makes sense.
Okay, I'm going fast. I know I'm going fast, which I hate. Okay. But just answer. I will do that next time on Wednesday. But did you understand where this came from?
Yeah, the Euler equation or whatever.
Well, yeah, e to the j omega t is what? It's cosine omega t plus j sine omega t. Yes?
Yeah.
You multiply this with the conjugate and divide by the conjugate. And then what? And then find the what? The real part and the imaginary part. And you do the Nyquist in exactly the same way as what? As we did a moment ago. But the major difference is what? Is that now we are interested in what? C. Remember the C? We are no longer interested in C in the right-hand side. We are interested in C being the number of roots of the, or the number of poles of the closed loop located outside the unit circle.
Yeah.
Did you get it?
Yeah.
Okay, but I ran out of time. I will show it to you next time. But the procedure is exactly the same. Did you get it or not?
Yeah.
Okay, but I will show it to you next time. Okay. Any question before I let you go?
I have a question, Professor.
Yeah.
Will you provide any practice problems?
Will I provide what?
Will you provide any practice problems?
Why you ask this question? Before every exam, I gave you practice problem. So, but in the final, I'm trying to make it clear to you. In the final, you need to make sure that you do have MATLAB running in your machine. You are not going to what? You are not going to do analysis by hand. Did you get it or not? Unless the question asked. So you need to make sure that MATLAB is running in your machine, and you need to know the MATLAB code for what? For Nyquist and Baudet. Did you get it or not?
Yes.
So you need to go what? You need to go to Google or ChatGPT, whatever, all of this fancy, and enter the following question. What is MATLAB code for to sketch the Baudet plot? What is the MATLAB code to sketch the Nyquist plot for both analog system and what? Digital system. Did you get it?
Yes.
And you can write it in your 8x11. And you have MATLAB running in your machine. You are going to generate, and then what? All the graphics, you are going to upload it into what? Into Canvas. There is no printer in the class. Did you get it? Now, I will bring it to you next time, some exam MATLAB examples of what? Of the Nyquist for both, Nyquist and Baudet, for both the discrete and for the continuous. Did you get it? And there will be what in the final exam? 3 problems. 1 in this root locus, 1 Nyquist, 1 Baudet. But I will tell you, choose 2. And if you do the third one, you will get extra credit. So you have 2 hours to solve 2 problems. Did you get it? No response. Did you get it?
Yes.
Hey, that's impossible, Professor. 2 questions in 2 hours. That's crazy.
Why is
I'm
crazy?
kidding.
It took me 2 hours. Didn't it took me 2 hours? And I keep saying yes or no, yes or no. You don't have to say yes or no. So that saves some time. Did you, by the way, don't forget to fill the course evaluation. Till now,
Oh,
nobody
yes.
filled it out. You need to fill it up.
I'm doing it right now.
Okay, good. What else? I missed today the race of the year because of this lecture.
The horse race?
Yes, the Kentucky Derby.
Oh, you watch horse races?
No, but only the Kentucky, only the three major ones. But
Oh.
otherwise,
Is
what
it
do
too
I?
late or is it over? Can you go now?
No, it's over right now. So if I see
Oh.
it, I will see just a recording. Yeah.
Sorry.
By the way, what do I know about horses? It just I want to see the hats. The older ladies, they wear nice hats.
Mm.
I don't know whether you have seen it or not in Kentucky Derby. They wear some
Yeah.
weird hats. Fancy, very
Yeah,
fancy.
yeah.
Yeah. Anyway, so I missed it. Anyway, that's fine. Life goes on.
Professor,
Yes.
for the course eval, I don't know if this applies to everyone too, but I don't see anything on my end. Like I don't see anything to fill out.
What didn't you get a notification?
I didn't get a
Yeah, actually, I'm looking as well, Professor. Your class is not one of the ones up for evaluation.
Please listen to me. Did you receive an email from the school?
Yes.
I didn't receive anything.
So what is this then I sent you? Didn't I send it to you?
You did. Here, this is the link to go to. I just sent it in the chat. If you want to do the
Okay,
evaluation.
1 second.
But yeah, but your
1
class
second.
is not one of them. But we'll do it for everyone else.
Is it possible that 500 level course there is no evaluation?
No, I have one for my other 500 level course. So I think it's just not for you this time.
Why? Is that
I don't know.
so I need to ask, but to who should I ask? I don't know.
I know that sometimes they don't. It's like it's only sometimes. You don't have to get evaluated on every course.
I don't know about that. So anyway, I would just bring it to their attention that there is nobody can see any evaluation for 580.
No.
No,
None
Professor.
of you. Okay, so I will contact them to see what is the problem. Yeah, and I will let you know. Anyway, okay, so you should have told me that when I emailed you first. You should have told me we don't see the link. Right now, I'm not sure. Maybe it's too late right now. I don't know. Anyway, who cares? But because it's a requirement, because then the department will think that I don't want you to write evaluation because you are going to say this professor is terrible or whatever. I don't care, but the department care. What you write is up to you. I will not be able to know who wrote what. But anyway, I will contact the chair lady to see what if there's a problem or not. What else?
Professor, when you gonna publish the midterm two exams marks?
Could you repeat that again?
When you gonna publish the midterm two marks?
My dear, I already just graded one. You wrote thesis. So big, only one, because I finished the other class. I teach 5 classes. You need to be patient. But I will give you the solutions on Wednesday. But the grades will be until I finish it.
All right, thank you.
You're welcome. What else?
I'm good.
By the way, did anybody know how many students showed up today? Do we get participants?
I saw like 12 or 13.
13.
Okay. Anyway, that's fine. If you know anybody who did not show up, let them know or give them the notes or whatever. By the way, I will make copies of the notes and I will pass it on Wednesday.
Will this recording also be uploaded? I see that
The
you're
recording, I will definitely send it to you. By the way, were we recording?
Yeah.
How do we know? Yeah, there is a red dot on the bottom, on the top, right?
I've also
That's
been
the
recording,
red dot?
Professor.
Huh?
Yes.
I've also been recording.
Yeah. But what I'm trying to tell you is I was online about 45 minutes before the class time. So when you see the recording, uh, uh, move a little bit after 45 minutes. I'm not sure. Did you get what I meant?
That makes sense.
I was online at 2:15 because I wanted to check the camera. It has been some time since I used this thing here from the COVID years. Did you follow me on that?
Yes.
Yeah.
So when you receive the recording, the first 30 minutes or 45 minutes, there will be nothing there. You need to fast forward to the start of the lecture. Don't email me telling me that there is nothing there. Did you get it? No response. Did you get it?
We will not email you, I promise.
Yeah. Yeah.
I gotcha.
Yes. Yuval, I got the invitation to the graduation. I appreciate that very much. But let's hope there will be some food. What else? Are you two guys are the only one graduating?
I think there's a few people.
No, in our class. Oh, by the way, before
Yeah.
I forget, how did the senior design go?
Oh, it went great. Jonah and I's team won the best display. I don't know if anyone who was in the best speech or oral presentation is in this class, though. I don't
What
think
I'm
so.
saying is that was there a prize for this?
There is a prize. I think they just tell you congratulations, you won.
Recognition.
Oh, recognition. So it means you cannot buy lunch with it.
I don't think so, unfortunately.
Okay, good. Yes. Okay. Congratulations. So you are done, both of you?
So we're done with senior design, and now, well, we got to finish classes. That's it.
I got that. What I'm saying is that there is no more behind that, behind this semester.
Yeah. No, this is it. This is it.
Okay. Okay. How about Betty? Did you finish? Betty? No, Betty. I think he left. Betty? Cannot hear. I will finish at 4. Okay, good. Okay, my dear. Let me go. I'm that tired. Any other question? Any other question? Any other question?
Nothing.
Okay, good. Okay, stay safe, stay healthy, and I will see you on Wednesday.
Sure.
Bye.
Have a great weekend, Professor.
You too. Bye bye.
Thank you.
Thank you.
You dear.
Bye,
Bye-bye.
Professor. Take
You
care.
are very welcome. Bye bye.